Welcome or welcome back, depending upon whether you watched the previous video or not. But considering that you did watch the last video, we ended the last video or the previous video by just laying off the foundation for glycolysis. So we wrote all these steps, all the enzymes, all the different associated things, and we lay the framework for the glycolytic pathway. What we are going to do right now in this discussion is that we are going to fill the gaps. Alright, so we are going to go into, or rather explore the details of each step of glycolysis. Okay, in a little bit more details, like not too much detail, a little bit. So nothing to be paranoid about. So this was the page where we left off, and it's looking quite messy. So we are going to pick off a new page, and this is essentially what the glycolysis looks like. And I think that everybody already knows all the different steps of glycolysis. And as far as any mnemonic regarding glycolysis is concerned, as far as remembering the steps is concerned, I have already said that I learned it the hard way. So I'm unable to help anyone. But it's pretty basic, so it can be easily understood, and it can be easily memorized also. We have to memorize this. Now we go into the details of the different glycolytic steps in this discussion. So what we are going to do now is that let's start with step 1 of glycolysis and see, or rather talk about the different details of the step 1. Okay, so step 1 of glycolysis. What was step 1 of glycolysis? Obviously, glucose was being converted to glucose 6-phosphate, right? Oh, sorry. Yes, now. So glucose to glucose 6-phosphate. Where is the phosphate coming from? Phosphorylation via ATP utilization, right? And the enzyme required was hexo or glucokinase, right? Hexokinase or glucokinase. Now, the most important thing to talk about in regarding this step is this hexokinase and glucokinase. So I had already talked a little bit about, not talked, I just said a sentence or two about this, that hexokinase and glucokinase are considered as isozymes of each other. So they are isoenzymic forms of each other, right? But they have their fair share of differences, right? Let's see what the difference between hexokinase and glucokinase is, or rather what are the differences between hexokinase and glucokinase. So bear with me. I'm making it won't fit here, would it? Okay, I'll abbreviate it. So this is hexokinase and this is glucokinase. All right, now listen to me very carefully. See, both hexokinase and glucokinase, I already said that they are isoenzymatic forms of each other. So they have the same job, they have the same function. What is the same function? Glucose to glucose 6-phosphate. This conversion is facilitated by this enzyme, be it hexokinase, be it glucokinase. Okay, but the difference between, the most primary difference between hexokinase and glucokinase is the fact that hexokinase has a lower Km value, whereas glucokinase has a higher Km value. From the basics of our knowledge on enzymes, which we will be exploring later in our later discussion. But we know that if an enzyme has a lower Km value, the affinity of that enzyme for the substrate is higher. So what is the substrate for hexokinase or glucokinase? It's glucose, right? So if hexokinase has a lower Km value, then obviously hexokinase has a higher affinity for glucose, whereas glucokinase has a lower affinity for glucose. Glucose being the substrate of these two enzymes. Okay, why this is important to know? Now see, if hexokinase has a higher affinity for glucose, that means that even when glucose concentration in blood is low, even when glucose content or concentration in blood is low, hexokinase will work. So even when glucose concentration in the blood is low, when glucose is low, when gluconeogenesis is favored, not glycolysis, but gluconeogenesis should be favored, even then hexokinase has such a strong affinity for glucose that even at low levels of glucose, hexokinase will work. But glucokinase having a higher Km value and hence lower affinity for glucose will only work when glucose concentration is much higher in the blood. Okay, so glucokinase is only induced, it is only induced when glucose concentration is very high in the blood. Okay, when glucose concentration in the blood is very high. Okay, so these are the primary differences between hexokinase and glucokinase. Okay, now there are some other differences as well. What? Hexokinase is the more, as you can already see, you can already kind of appreciate the fact that hexokinase works at all glucose concentrations. Even when it is low, hexokinase will work because it has a very strong affinity for glucose. So it is only obvious that hexokinase is the enzyme which is present in almost all tissues, right? Because it has such a strong affinity for glucose. So almost all tissues in the body will have hexokinase because glycolysis is universal, right? But glucokinase will only be present in the hepatocytes, that is in liver. Okay, only in liver. And that makes sense because we know that when glucose concentration is high, liver has a large role to play in bringing that concentration down to normal. And since liver has a large role to play, via insulin and other hormone or other actions of liver by which it will bring down glucose concentration, one of that action is glucokinase inducing. Because if glucokinase is induced, then glucokinase will act on the glucose, high concentrations of glucose, it will act on that. And if it will act on the glucose, glucokinase is an enzyme of what? Glycolysis. So glucose will start breaking down because glycolysis is the catabolism of glucose. It's a catabolic pathway. It's breaking down of glucose, right? So it's very evident why glucokinase being activated when glucose is higher is actually present in liver. See, these 2 points are related. That's what I'm trying to point out, that these 2 points are related. Okay. Now, I said something about glucokinase being induced when glucose concentration is high. As you can all appreciate, something else is also induced when glucose concentration is high. Something very common, a very common hormone. Yes, insulin. Insulin. So not only does higher concentrations of glucose induce glucokinase, insulin also induces glucokinase. Very, very important. Insulin also induces glucokinase because insulin is also tasked with bringing down glucose concentrations in blood. And glucokinase is one of the components for doing just that, right? So insulin induces glucokinase. However, hexokinase always works. It is not inducible. Okay? So it's not like hexokinase is induced by a particular substrate or particular hormone or anything else, right? It always works. And that's why we can all appreciate that it will work even when glucose concentration is very low. So see, what I'm trying to point out here are not individual points of differences. They all together make up a profile. That's what I'm trying to point out here. That all the points here, they're related to each other. Right? And this connectivity is what will help in us retaining this information. Otherwise, 2 months later, when you have not studied, when for a long time you have not revised, suppose, this glycolysis part, even then you will be able to recollect from logical perspective that hexokinase should be this, and glucokinase should be this. Alright? Alright. So, as far as inducing capabilities or being induced is concerned, hexokinase is not inducible, it's not induced, whereas glucokinase is induced by insulin and obviously glucose itself. Right? Right. So, now these are the primary differences between hexokinase and glucokinase. So accordingly, depending upon what the concentration of the glucose is in the blood, what the state of the body is, hexokinase or glucokinase will be used. Okay. Another very important thing I would like to talk about here is, we said that insulin induces glucokinase. We said that, right? So what's the counterpart or the reciprocal hormone of insulin? What is the hormone that does exactly the opposite of insulin? Glucagon. So insulin induces glucokinase, glucagon will actually inhibit glucokinase. Okay, we'll talk about this later in detail when we'll be talking about the inhibition or the regulation of glycolysis, right? But we will see that hexokinase is not affected by insulin or glucagon. Rather, it is actually inhibited. If it has to be inhibited, then hexokinase is inhibited by glucose 6-phosphate itself. So glucose 6-phosphate is the product. Product inhibition works on hexokinase. Product inhibition works on hexokinase, and that is the only thing that can inhibit hexokinase. Unlike glucokinase, which is affected by third-party factors like insulin, glucagon, etc. We'll talk about this again when we talk about regulation. I just mentioned it. So that's about hexokinase or glucokinase. Now obviously we can all appreciate that one molecule of ATP is being utilized here and ADP is being formed. So glucose is actually being phosphorylated to form glucose 6-phosphate, and we can all appreciate the fact that this is an irreversible step. Okay, so this is an irreversible step. Reversibility of the steps, whether a particular step of glycolysis is reversible or irreversible, is very important and should obviously be kept under consideration. Okay. Now let's talk about the second step. The first step was pretty important, that's why I took so much time. So second step, we all know that glucose 6-phosphate is reversibly converted into fructose 6 phosphate, right? And obviously the enzyme used here is phosphohexose isomerase. So phosphohexose isomerase, that is the enzyme that is used here. And obviously this is a reversible step. Done. And nothing much to talk about this actually. That's that. Third step. So the first step was pretty important, right? Now the third step again is important, very important. What's the third step? Fructose 6 phosphate is irreversibly converted to, or rather phosphorylated to, fructose 1,6 bisphosphate. Very, very important step. This is considered as the key, the most important regulatory step of glycolysis. So it's important. Now we'll talk about regulation later, as I've already mentioned. So then we will explore. But let's talk a little bit about it now. Fructose 6 phosphate is irreversibly converted, or rather phosphorylated to fructose 1,6 bisphosphate, and hence we need a phosphate source, and obviously the source is none other than ATP, one molecule of ATP being converted to one molecule of ADP. The enzyme which is used here is obviously from fructose 6 phosphate to fructose 1,6 bisphosphate, so we need a kinase, right? So phosphofructokinase, abbreviated as PFK, phosphofructokinase. This enzyme is very important, okay? And since phosphofructokinase, I had already mentioned one thing about phosphofructokinase in the previous discussion. I still remember it, although I recorded it 1 week earlier. So phosphofructokinase has two isozymes, okay? It has two isoenzymatic forms. One is PFK1 and the other is PFK2, okay? This conversion in glycolysis itself, the thing that is happening, that is fructose 6 phosphate to fructose 1,6 bisphosphate, this very conversion is brought about by PFK1, not PFK2, PFK1, okay? Then what's the job of PFK2? We'll talk about PFK2 just a little bit later, okay, when we talk about regulation. So we are building up a lot for regulation, right? Okay, so PFK1 is the enzyme which is used for fructose 6 phosphate to fructose 1,6 bisphosphate, and it's a very important enzyme. It's a key enzyme. See, whenever there is an irreversible step in a particular pathway, we say that those irreversible steps are the rate determining or rate limiting steps. So a rate limiting step of a particular pathway is considered as the most important step, and glycolysis has 3 rate limiting steps. So once we chalk down all the steps, we'll summarize. When we'll be summarizing it, we'll talk about it, okay? Now we have completed 3 steps of glycolysis. These 3 steps: step 1, glucose to glucose 6 phosphate, step 2, glucose 6 phosphate to fructose 6 phosphate, and fructose 6 phosphate to fructose 1,6 bisphosphate. These 3 steps together, they are known as the preparatory phase. Alright? Preparatory phase. Oh my god, I'm sorry. RATORY. I'm sorry. Preparatory phase. These three steps together, they are known as the preparatory phase of glycolysis, and rightly so, because you see, from step 1 to step 3, these three steps, in these three steps we are seeing that ATP is being used up. It is being used up, not in this step, but since this is in between these two steps, so it is considered as together as the preparatory phase. So preparatory, we are preparing for the next steps to come, so that in the next steps we can build ATP rather than break ATP. So these three steps together are the energy consuming part of glycolysis. So they are together known as the preparatory phase of glycolysis, as if we are preparing for the synthesis of ATP phase, which will come on the subsequent steps. Okay, done. Now step 4, quickly, yes, it's visible. Step 4. So we have now formed fructose 1,6 bisphosphate. Now is the time to split the 6 carbon compound into 2 3 carbon compounds. So fructose 1,6 bisphosphate is reversibly split into 2 things. The first is glyceraldehyde 3-phosphate, and the other is dihydroxyacetone phosphate. Okay, these are the 2 compounds which are formed, right? Fructose 1,6 bisphosphate had 2 phosphates, right? That's why in the first carbon and in the 6th carbon, so 2 phosphates. And see, glyceraldehyde 3-phosphate 1 phosphate, and dihydroxyacetone phosphate 1 phosphate. So the phosphate has also been cleaved, or rather not cleaved, I'm sorry, the 2 phosphates have been distributed in the products being formed, right? So now the enzyme which is concerned with this is aldolase. Okay, aldolase is the enzyme which is actually facilitating the splitting of fructose 1,6 bisphosphate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Now, as I have already mentioned, that this reaction is reversible. Another thing that I'm trying to mention here is that aldolase is also another enzyme which has 2 or rather more isoenzymic forms, namely aldolase A and aldolase B. Okay, these are 2 isoenzymatic forms of aldolase. Alright, so there is aldolase A and there is aldolase B. Now listen to me very carefully. See, aldolase A is the enzyme or is the isoenzymic form which is actually facilitating the splitting of fructose 1,6 bisphosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, right? And aldolase B will be used when we will talk about fructose metabolism. See, we are talking about glucose metabolism right now, right? This is glycolysis, but glycolysis here is the normal glycolysis, that it is starting with glucose as the substrate. But we will see that the starting substrate may not be glucose, it might be fructose or it might also be galactose. So in those cases, what happens? Alright, we'll see that in just a little bit time. So fructose 1,6 bisphosphate, glyceraldehyde 3-phosphate, dihydroxyacetone phosphate, aldolase, 2 isoenzymatic forms, aldolase A and aldolase B. Alright, and this is aldolase A which is doing this reaction. Okay. Now let's talk about the 5th step. Alright, the 5th step will actually be the conversion of, this is step 5, I'm writing here, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, they are interconvertible. Okay, they are interconvertible, but what happens is that dihydroxyacetone phosphate, the one molecule of dihydroxyacetone phosphate which is formed from fructose 1,6-bisphosphate is actually converted to one molecule of glyceraldehyde 3-phosphate. That is step number 5 of glycolysis. Okay, so dihydroxyacetone phosphate is converted to glyceraldehyde 3-phosphate. So we had already got one glyceraldehyde 3-phosphate from fructose 1,6-bisphosphate, and now we are getting another glyceraldehyde 3-phosphate from dihydroxyacetone phosphate. So 2 glyceraldehyde 3-phosphate we will have. Okay, hence all the subsequent steps that will take place from now on, they will actually occur twice, because there are 2 molecules now, 2 molecules or 2 substrates. Both of them are glyceraldehyde 3-phosphate. So 2 molecules of glyceraldehyde 3-phosphate will be metabolized. So everything from now on will be multiplied by 2. Okay. By the way, the enzyme here is, see, this is dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, right? They are actually isomers of each other, right? So isomerase, phosphotriose isomerase is the enzyme which is used here. Okay, right? So phosphotriose isomerase. Now let's move on to the next step, which is step number 6. So step number 6 is essentially, we have now got glyceraldehyde 3-phosphate, right? Now listen to me very carefully. Step 6 is again important. Okay, this glyceraldehyde 3-phosphate, I am abbreviating it GLY, glyceraldehyde 3-phosphate, right? This is actually, what is done is again reversibly converted into glyceraldehyde 3-phosphate to glyceraldehyde, or rather I'm rewriting this, 1,3-bisphosphoglycerate. Very, very important step. Glyceraldehyde 3-phosphate, we already had that. Reversibly, that is converted into 1,3-bisphosphoglycerate or 1,3-BPG, abbreviated form, 1,3-BPG. So now obviously let's get on with the fill in the blanks part. The enzyme here, before talking about the name of the enzyme, we have to talk about what happens in this step. See, glyceraldehyde 3-phosphate is being converted to 1,3-bisphosphoglycerate, right? So think here. Firstly, there are two things happening here. First thing, phosphorylation is happening. Phosphorylation is occurring. Second thing, this was glyceraldehyde and this is glycerate. Glycerate means glyceric acid. Are you getting me? This is basic organic chemistry. We already have done a little bit of organic chemistry in our high school, right? This is glyceraldehyde 3-phosphate. This is an aldehyde. And this is 1,3-bisphosphoglycerate. It's an acid. So if we have to convert an aldehyde to an acid, then by the basic organic chemistry knowledge, we can say that what is happening here? What's happening here? Oxidation is occurring here. Yes, because we know this chart. Remember this, or we already know this actually, that if there is an alcohol, converting that alcohol into an aldehyde is oxidation. Again, converting the aldehyde or rather if we oxidize the aldehyde, we'll get a carboxylic or an organic acid, right? So this is the trend. And again, if the other side is to occur, then this will be reduction. This is basic organic chemistry, right? So here we have an aldehyde, glyceraldehyde, and 3-phosphate, which is phosphorylated. Aldehyde, we are getting an acid here. So what is this happening here? Aldehyde to acid is oxidation. So this is oxidation, right? So if oxidation is to occur, then we need something to facilitate that oxidation, right? That something is none other than an oxidized coenzyme, that is NAD+. NAD+ will be converted to NADH plus H+. So see, NAD+ was the oxidized coenzyme. It itself got reduced. So this is reduction. This step is reduction. This NAD+ is facing reduction, right? So the coupled reaction, this reaction will face what? Oxidation, because we know that reduction and oxidation, they are always coupled. Yes, that's why they are known as redox reactions, right? So NAD+ is what's occurring with NAD+? Yes, it is being reduced, so reduction. So what will happen with glyceraldehyde 3-phosphate? It is oxidized. That's why these are coupled together. So glyceraldehyde 3-phosphate is oxidized to 1,3-bis-phosphoglycerate, but like I said, this is not the only thing that's happening. The first thing that is also happening is phosphorylation is also occurring. Now remember, I said that in the subsequent or in the previous steps, for example, from glucose to glucose 6-phosphate, or from fructose 6-phosphate to fructose 1,6-bisphosphate. These were also phosphorylations, right? What was the source of the phosphorylation in those steps? ATP. But I have already mentioned something, that those 3 steps, step 1, step 2, step 3, where ATP was being consumed is over. That's the preparatory phase, it is over. In the subsequent stages or subsequent reactions, there will be no ATP utilization. So we can be sure that the source of the phosphate for glyceraldehyde 3-phosphate's phosphorylation is not ATP. Then what is it? Very simple. It's just an inorganic phosphate. It's an inorganic phosphate. It does not have any fixed source. It's not coming from a very particular molecule or compound. It's just coming individually. So NAD+ and an inorganic phosphate, both are being added. So this is inorganic phosphate. Alright? It's not coming from ATP because preparatory phase is over. Then splitting phase is also over. Splitting, that 4th and 5th step, those two were considered as the splitting phase. Now we are actually, these steps subsequently, they will be the ATP forming step. They will be the ATP formation step, right? So they will be the payoff phase. Payoff, like you worked so hard, you prepared so much, now is the time that it will pay off. Your hard work will pay off. And yeah, his hard work is paid off because ATP will be formed, right? So see, there is logic in the name, right? So now, what will be the name of the enzyme? So I said all of this and now I will tell the name of the enzyme because now it will make sense. So what is this happening here? Dehydrogenation, yes, because hydrogen is being removed from this compound and hence it is being oxidized. So a dehydrogenase. So glyceraldehyde 3-phosphate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase. hydrogenase is the enzyme which will be used. Okay, lovely, very good. Now, so this is that done. Okay, now let's move on to step 7. Step 7 is also important because 1,3-bisphosphoglycerate is being converted 1,3-bisphosphoglycerate is being converted, I am sorry, this is reversible as well, to 3-phosphoglycerate. Okay, 1,3-bisphosphoglycerate is converted to 3-phosphoglycerate. So we had, do not confuse glyceraldehyde 3-phosphate and 3-phosphoglycerate. This was something that used to happen with me. So I'm speaking from a common experience here. 3-phosphoglycerate, this is an acid, and glyceraldehyde 3-phosphate is an aldehyde, right? So do remember that. Okay, so 1,3-bisphosphoglycerate is being converted to 3-phosphoglycerate, and the enzyme here is bisphosphoglycerate kinase or phosphoglycerate kinase, bisphosphoglycerate kinase. Done. So that's the name of the enzyme here. Now this is one such step where you can see very clearly that 1,3-bisphosphoglycerate had 2 phosphates and 3-phosphoglycerate has only 1. So where did the other high energy phosphate bond go? Yes, it was used in the formation of ATP. Hence this is the payoff phase, right? This is the payoff phase. That's why, because ATP is now being formed. Okay, done. So this ATP is being formed. Look at something very carefully. Obviously this is an example of, we can say, to be phosphorylation, because phosphate is being transferred, right? Now we know that there are 3 forms of, there are 3 forms of phosphorylations by which ATP is formed. This is something that is actually taught in high school, biology, botany. There are 3 forms. What are they? One is known as oxidative phosphorylation, right? The other is known as substrate phosphorylation, and the last one is known as photophosphorylation. So here these phosphorylations actually refer to, in these cases, the phosphorylation actually refers to the formation of ATP. We know that phosphorylation means phosphorylating something, like you're adding phosphate to something. But when we are actually mentioning oxidative, substrate, photo, that only means that you're talking about the formation of ATP, and hence in that scenario you're talking about phosphorylation, not in any other scenario. Okay, am I being clear? Okay, so these 3 are ways, phosphorylation ways in which ATP is formed. ADP is phosphorylated to form ATP. So ATP, we all know that it's actually a form in which energy is trapped, right? So oxidative phosphorylation is the way in which something is oxidized and the energy released is used in the form of, or energy released is trapped in the form of ATP. For example, we'll see already later, electron transport chain. That's example of oxidative phosphorylation. So we are using the redox potential and the fact that the different intermediates are moving down their redox potentials, and hence energy is being released. That released energy is being used to form ATP or being trapped in the form of ATP. That is oxidative phosphorylation. Right? ATP is being formed from the oxidation of something else. Substrate level phosphorylation is occurring, or rather we say that it occurs when from a particular substrate itself, directly ATP is formed. So there is no subsequent process which is required, oxidation or photons striking it or something happening. No, direct, like this over here. See, this is also an instance of ATP being formed, right? So this also has to come under one of these three. This here is an example of substrate level phosphorylation, where we can already see the substrate was 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate actually donated one of its high energy phosphate bonds to ADP directly. So ADP got its phosphate to form ATP directly from the substrate. Hence, this is known as substrate level phosphorylation. The last one is photophosphorylation, which is not something which is related to us humans, is related to botany, that is the plants. Plants require, or rather utilize, photophosphorylation. Photon, light. So they actually use light energy and trap it in the form of, we have already read a little bit about it when we read about photosynthesis in botany in our high school. So that was example of photophosphorylation. Not going into the detail obviously, because I don't remember the details. So this is substrate level phosphorylation. Okay, so this is very, very important. Done. Now let's move on to step 8. Step 8 is 3-phosphoglycerate being converted to 2-phosphoglycerate. So it's pretty simple. The phosphate was in the third carbon, that was shifted from the third carbon to the second carbon, forming 2-phosphoglycerate. Simple. So are 3-phosphoglycerate and 2-phosphoglycerate isomers of each other? Not really. They are actually what we, in these cases where just shifting of one thing, shifting of a particular group occurs from one carbon to other, from one particular side to the other, just that, 3 to 2, 2 to 1, something like that. Here most of the times the enzyme used is mutase, as if a mutation has occurred. Mutase. So the enzyme is phosphoglucomutase. Phosphoglucomutase. And obviously this is this is a reversible step. Done. Now step 9. Step 9 is 2-phosphoglycerate to 2-phosphoenol pyruvate. Very important. This is another important step, very important step. 2-phosphoglycerate to phosphoenol pyruvate. Firstly, something that you have to remember immediately, since this is so unique, the thing that I'm about to say is that one molecule of water is released. In no other step in glycolysis, water is even remotely associated. Water as a molecule, remotely associated, no, in no other step. Only in this step, step 9. That's why it's so unique. You should immediately remember, this should immediately strike, that 2-phosphoglycerate to phosphoenol pyruvate. Oh yes, the step in which one molecule of water is given out. Yes, this is an identifying feature, right? Also another identifying feature is the fact that okay, I'll talk about that later, a little bit later. So what's essentially happening is that 2-phosphoglycerate is converted to phosphoenol pyruvate, and the enzyme used here is enolase. So yeah, one thing that you can talk about, which I was saying that we may remember, is that enolase, the enzyme, it's a pretty unique name. So that too is a distinguishing feature, right? Like till now you were all listening to names like dehydrogenase, bisphosphoglycerate kinase, phosphoglucomutase, enolase. That's a simple name compared to those. So yeah, that's good, right? So enolase, this enzyme is very I can say distinct, because enolase requires magnesium ions. Now I have already said that most kinases, almost all the kinase enzymes in glycolysis require magnesium ion. Not only in glycolysis, like kinases as a enzyme group require magnesium as cofactor, right? They require that, and I had already also talked a little bit about why they require that. They form a complex with the magnesium, and the activation energy is lowered and stuff like that. But enolase also requires magnesium, and why you should remember this, why I am stressing on this information, is because, listen to me very carefully, enolase can be inhibited by fluoride. So although I have not talked about inhibition, but let me talk about it here itself. So enolase is inhibited by fluoride. You know, fluoride ion, yes, that fluoride. How fluoride inhibits enolase, the enzyme, is that fluoride will actually remove the magnesium ions, because fluoride is extremely reactive. I think what happens is that, this is something I have not read in any textbook, but I think what happens is that fluoride ion extremely reactive, very reactive species. So when you add that, it will automatically react with magnesium. It should. Ions, right? They should. So it will kind of suck out the magnesium. So enolase without magnesium will be irreversibly inhibited, completely gone. So this step will not occur. Now if this step does not occur, glycolysis cannot complete. Glycolysis cannot complete. Why this is important, very important clinically, is because this is actually employed when blood is stored in vials. I'm sorry, not vials, vials, you know, where they store blood, right? So for example, for testing out blood glucose, we have to first, you know, take out the blood, extract the blood, right? Take a blood sample from the patient, and those are stored in vials in the labs, right? Now the problem is that if the glucose concentration or content in the blood, if that glucose starts being metabolized by the cells, by the erythrocytes, because erythrocytes have only glycolysis as the only medium by which they can produce energy. So if the erythrocytes start utilizing that glucose which is present in that vial, or in the blood sample rather, then that would give faulty reading later, because glucose originally would be lower than the original reading, or what should have been the content, because erythrocytes have already metabolized a part of the glucose for their own survival, maybe. To stop that, to get a more accurate reading, what's done is fluoride is added to those test vials, right? And so what will happen is that fluoride will actually inhibit enolase by the way that I have just talked about, and this step will not occur. Glycolysis itself will be blocked off, so we'll get a more accurate reading. Done. So that's how fluoride will work. Now let's talk about the last step of glycolysis, step 10 of glycolysis. Phosphoenol pyruvate will be irreversibly converted, so again we get an irreversible step, irreversibly converted to pyruvate. Okay, phosphoenol pyruvate to pyruvate, and the enzyme is pyruvate kinase. And again, as you can all see, phosphoenol pyruvate. So there was a phosphate, but in pyruvate that phosphate is missing. So obviously the phosphate was used for the purpose which it can be used for in the preparatory, or rather payoff phase, ATP formation. Logical? So this is another step where substrate level phosphorylation is taking place, and hence this is also irreversible step, so another important feature, and hence this is also one of the key glycolytic enzymes and rate determining step. Okay, so this is also one of the steps which is very important as far as the regulation of glycolysis is concerned. Done. So we formed pyruvate, and that stops, or rather that is the end of actual glycolysis. After that, what happens is, depending on oxygen concentration, depending on oxygen availability, aerobic or anaerobic conditions, this pyruvate can be utilized for the Krebs cycle via oxidative decarboxylation, which we will talk about in subsequent discussions later, or in anaerobic conditions. We have already talked about it, so no suspense building. It's actually used for forming lactic acid or lactate by the enzyme lactate dehydrogenase. So it forms lactate, and this is reversible as well. Lactate dehydrogenase. Okay, done. So pyruvate to lactate. Now think about it. Not really to think about it. I can't give you a logic for this until we know the actual structures and what the organic chemistry is going on, the molecular thing is going on. Without that, we can't talk about it. But we can say that from pyruvate to lactate, essentially what's happening is that NADH plus H plus is being converted to NAD plus. NADH plus H plus, which is a reduced form, is being oxidized to NAD plus, just the opposite of what had happened earlier, right? So in this step, pyruvate is reduced to lactate. Pyruvate is reduced to lactate, and the reduced coenzyme NADH plus H plus is oxidized to NAD plus. See, there is a very important significance of this step. Not only is the fact that this happens in the fast working muscles and lactate accumulates and all that stuff, which we'll talk about just now, but also the fact that, see, we already saw that NAD plus here, NAD plus, this is required. This is very much required for glycolysis. So we require coenzyme for glycolysis to actually continue, for this step to occur. However, the availability of coenzymes in the cell is very limited, restricted. So if we do not have a supply of NAD plus, if we do not have a proper supply of NAD plus, then this step cannot be occurring, and the entire glycolysis will be shut down at that part, right? That will be a problem. So this is called bottleneck effect. When there is a large problem, when there is a large pathway, and in a particular step of that pathway, something is there which is limiting that step, and hence limiting the entire pathway. That part is called the bottleneck effect, and this is something which is it's a general English term, bottleneck, right? It's restricting that entire thing, which is otherwise okay, which is otherwise normal, but only that small thing is being the problem, right? So in case of computers, we use, for example, when we start playing any game, we say there is a GPU bottleneck, or there is a RAM bottleneck, there is a CPU bottleneck. So the game's system requirements, as far as that is concerned, we suppose somebody has a very good RAM, but the GPU is a problem, the graphics card is a problem, the GPU is a problem, then we say that that person has a GPU bottleneck. So this is only for the people who are into such kinds of things. So but I hope you understand what bottleneck means. Okay, so that's a problem. So NAD plus has to be what? Brought, supplied. So what happens is that this NADH plus H plus which is formed, this is reconverted to NAD plus at the end, pyruvate to lactate, and the NAD plus is again channeled back to the 6th step. Okay, done. So what happens in case of aerobic cases? In aerobic cases, in the Krebs cycle itself this will happen. We know that in the Krebs cycle itself it will happen, and actually what happens is that in aerobic condition, oxidative phosphorylation will later occur itself. So we don't have a problem with bottleneck, but this will occur in anaerobic cases because oxygen is not available, so oxidative phosphorylation cannot take place. So NAD plus is required. It is very highly required. So NAD plus can cause a very big problem in anaerobic cases due to the bottleneck effect. Okay, done. Now let's just summarize in a few sentences what happened. Not what happened, rather I'd say the different points. The first thing which I would like everybody to remember is that steps 1, 3 and 10, these 3 steps, according to the number which I had put, you will see that in the textbooks I had seen that they actually consider the actual glycolysis to be 9 steps, and they consider lactate formation as a part of actual glycolysis. But I personally think, and from what I have we all have studied in high school botany, that glycolysis is up to pyruvate formation. Whatever happens with pyruvate shouldn't be a part of glycolysis, because it defeats the definition or purpose of glycolysis, or what we define glycolysis to be, right? So according to what I had put, steps 1, which is glucose to glucose 6-phosphate, step 3, which is fructose 6-phosphate to fructose 1,6 bisphosphate, and step 10, which is the last step, phosphoenol pyruvate to pyruvate. These 3 steps are irreversible. They are irreversible steps. Okay, all the other steps are reversible. Done. Steps 1, 3, 10 and 7, 1, 3, 7 and 10, these are the 4 steps where ATP is either formed or utilized. In the first 2, which is 1 and 3, steps 1 and 3, ATP is utilized. Okay, whereas in steps 7 and 10, ATP is formed. Okay, so 1, 3, 7, 10, ATP is formed. Okay, done. Now third thing which I would like to talk about is the energetics. Very simple, very simple. See, we all know that 1 and 3 here ATP is being utilized. So in step 1, 1 ATP is utilized. In step 3, 1 ATP is utilized. So 2 ATP used. Overall 2 ATP is used. In step 7, 1 ATP is formed, and in step 10, 1 ATP is formed. So 2 ATP formed. But I had said that after the splitting, which was essentially step 4 and step 5, that glyceraldehyde 3-phosphate and dihydroxyacetone phosphate being formed. After that, we have to multiply everything by 2 because there are 2 molecules of glyceraldehyde 3-phosphate. One is directly from fructose 1,6-bisphosphate and the other was dihydroxyacetone phosphate being converted to glyceraldehyde 3-phosphate. So there are 2 molecules of glyceraldehyde 3-phosphate. So from there we have to multiply everything by 2. So 2 ATPs being formed, 7 and 10 will be 2 into 2, that is 4 ATPs being formed. So 4 ATP being formed. So overall we get a net gain of 2 ATPs. Okay. So 2 ATPs positive, that is we gain 2 ATP. And this is the story of anaerobic glycolysis. The glycolysis which is followed by the lactate formation. Anaerobic cases. 2 ATPs done, nothing else. But in aerobic cases, something else also needs to be taken care of. I had said that 1 NAD plus to NADH plus H plus is also being formed. So 1 NADH plus H plus is formed. Now when oxidative phosphorylation, we'll be talking about that, when we're talking about the electron transport chain, we will find out that 1 NADH plus H plus, one reduced coenzyme will give rise subsequently, how we will see that later, will subsequently give rise to 2.5 ATPs. 2.5 ATP. But is there only 1 NADH plus H plus being formed here? No. 2 into 1, yes, because NADH plus H plus is being formed in the step. Which step? It was step 6. Right? Right? So we have to multiply that by 2. So 2 into 2.5 ATP being formed subsequently later, not directly from glycolysis but subsequently. So 5 ATP. So in aerobic cases, we get a net gain of 7 ATPs. Whereas in anaerobic cases, we get a net gain of 2 ATPs. From glycolysis. Okay. Now, something which actually confused me personally a lot was that when I had studied this same thing in high school, botany, we had been taught that 1 NADH plus H plus gives rise to 3 ATPs, not 2.5. So after coming, or rather after reading the biochemistry book, when I first came to know that it was 2.5 ATPs, I was very confused. And nowhere it was mentioned that 3 ATPs, no, it's actually 3 ATP or something like that. So I was very confused. And later I found out that the 3 ATPs, and hence I'm actually clearing this up. Later I found out that the 3 ATPs being formed from 1 NADH plus H plus is an old calculation. It's an old concept. Now, new or a modern concept is 2.5 ATPs being formed, not 3. So subsequently, we used to, this also used to come in the medical examination, like the joint entrance examination. How many ATPs being formed? 38 ATPs or 36 ATP, depending on the shunt, depending on which shunt pathway we are being used. So 36 or 38 ATP, but actually it is 32 ATPs overall, like considering glycolysis, Krebs cycle, oxidative phosphorylation, everything. 32 ATPs. So we'll deal with those later, but this is an important piece of information. That is 2.5 for 1, not 3. Okay, so at least this confused me a lot. Maybe you guys knew it from before itself, I don't know. So yeah, that's that. Now we have essentially covered the details of glycolysis. The thing that remains is the small part of not inhibition, I would say regulation. See, regulation of glycolysis is very important. No doubt about it. It is very important. So regulation of glycolysis, the first thing that I would like to say is that where can glycolysis be regulated? In what steps is glycolysis being regulated. In the irreversible steps, glycolysis is regulated. So it is only in the steps 1, 3 and 10 that the actual regulation of glycolysis takes place. So those are the rate determining key steps of glycolysis. Okay, so let's first talk about the first step, which is glucokinase or hexokinase catalyzed glucose to glucose 6 phosphate. Right. So I have already mentioned this, that hexokinase is only inhibited by its product, that is glucose 6 phosphate, whereas glucokinase is actually inhibited by glucagon, whereas it is activated or induced by insulin. Okay, and obviously how and why that happens, I've also mentioned that, right? Second thing, which or rather, let's write it like this: third reaction, this was the first reaction, third reaction regulation, how that occurs. So what was the third reaction? Let's talk about that first. That was the step catalyzed by phosphofructokinase, that is fructose 6 phosphate to fructose 1,6 bisphosphate. Now listen to me very carefully, this is an important one. I had said that this is catalyzed by phosphofructokinase 1. Okay, phosphofructokinase 1. The first thing that you have to remember, let me use a different page here. The first thing that you have to remember, first thing, is that phosphofructokinase 1, this is actually induced, positively induced by a compound which is fructose 2,6 bisphosphate. Very, very important. Fructose 2,6 bisphosphate is actually positively inducing phosphofructokinase 1. So it's an activator of PFK1. Why you should remember this and how you will remember this, I'll tell you. What does PFK1 facilitate? The formation of fructose 1,6 bisphosphate, right? So just the mutase form, that is, instead of fructose 1,6 bisphosphate, I'm saying fructose 2,6 bisphosphate. Fructose 2,6 bisphosphate is an activator or inducer of PFK1, this molecule, this compound. Please remember this, fructose 2,6 bisphosphate. Now I'll tell you how this ties up with the PFK2. So let's write it down. See, we have fructose 6 phosphate, okay, being converted to fructose 1,6 bisphosphate. Here phosphofructokinase 1 is being used. Okay, now phosphofructokinase 1 is positively induced by, I have already mentioned, fructose 2,6 bisphosphate. But where is the fructose 2,6 bisphosphate itself coming from? Where is fructose 2,6 bisphosphate coming from? And hence inducing positively PFK1. Where? From how is this coming? This itself is coming from, yes, fructose 6 phosphate itself. Very important. And this is reversible. Okay. So this itself is coming from fructose 6 phosphate. Very, very important. And do you know what the enzyme which facilitates this conversion is? Yes, PFK2. Very, very important. I have said very, very important for at least 30 times in this discussion, because everything is very important and I'm very paranoid about details. So PFK2 is the enzyme which catalyzes the formation of fructose 2,6 bisphosphate from fructose 6 phosphate hence positively inducing PFK1, so that the subsequent, the other fructose 6-phosphate molecules can be facilitated, or rather their conversion to fructose 1,6-bisphosphate can be facilitated. Am I clear? Am I clear? Okay, this is what is happening. But fructose 6-phosphate, fructose 2,6-bisphosphate, what we need here? Yes, we need an ATP. We need one molecule of ATP here. Okay, so one molecule of ATP, because the phosphorylation needs to take place, right? So that's that. Okay, so fructose 2,6-bisphosphate will positively induce phosphofructokinase 1, and obviously ATP is being utilized in this step, we know that. So hence fructose 2,6-bisphosphate is a very important activator. Okay, but fructose 2,6-bisphosphate, as I have already mentioned, is an important activator of PFK1, no doubt about that. It not only does it positively induce PFK1 directly, and it has another important function. That is, there is this enzyme called fructose 1,6-bisphosphatase, and what this enzyme does is, it will essentially convert fructose 1,6-bisphosphate, it will dephosphorylate it and form fructose 6-phosphate. That is just the opposite of this step, and the opposite of this step takes place in gluconeogenesis, right, when glucose has to be formed. So fructose 1,6-bisphosphatase is a gluconeogenesis favoring enzyme, but fructose 2,6-bisphosphate, what it will do is, it will negatively induce fructose 1,6-bisphosphatase. So gluconeogenesis favoring enzyme will be negatively induced, and hence gluconeogenesis is inhibited and glycolysis is favored. So this is another way in fructose by which fructose 2,6-bisphosphate works. Okay, now I have said that if gluconeogenesis has to be or rather glycolysis has to be favored, then this happens. What happens in the other way round? See, glycolysis is favored when glucose concentration is high, very high. So if glucose concentration is very high, then obviously the body will try to metabolize it, and hence glycolysis will take place. So this will only occur when glucose is very high. What happens if glucose is very low? Then gluconeogenesis is favored. So glucose has to be formed. Then what happens is very important. See, there is this another enzyme called fructose 2,6-bisphosphatase, and what fructose 2,6-bisphosphatase will do is, it will convert fructose 2,6-bisphosphate back to fructose 6-phosphate. Okay, so it will convert this back to fructose 6-phosphate. Essentially, fructose 2,6-bisphosphate would have positively affected PFK1, and hence this would have, glycolysis would have been favored. But since fructose 2,6-bisphosphate itself is being converted back to fructose 6-phosphate, so glycolysis is not favored. On the other hand, the opposite, which is gluconeogenesis, is being favored. So that occurs when there is excess, when glucose actually is low, not excess, when glucose concentration is low, gluconeogenesis will occur. Okay, so we can say that PFK2 and fructose 2,6-bisphosphatase are reciprocal enzymes, because PFK2 has the task of phosphorylating fructose 6-phosphate and forming fructose 2,6-bisphosphate, whereas fructose 2,6-bisphosphatase enzyme has the task of dephosphorylating fructose 2,6-bisphosphate and forming fructose 6-phosphate. So they are reciprocal, and hence they are activated at different scenarios. So PFK2 is activated by the process of dephosphorylation, by the way, which we will study later when we talk about intracellular receptors and hormones and signaling. When we talk about that, we'll talk about that. But PFK2 is activated when glucose is high, as I've already mentioned, and fructose 2,6-bisphosphatase is activated when glucose is very low. Okay, and by the way, other positive effectors are insulin, because obviously AMP is a very important positive effector, and I actually didn't research as to why that is the case, so I'm sorry about that, but I'll see to that later. Okay, fructose 6-phosphate, because it is the substrate itself, so substrate itself will obviously positively induce PFK2 obviously, and fructose 2,6-bisphosphate also obviously, right? These are the positive effectors of PFK1. Negative inhibitors, negative effectors, they are glucagon obviously. Instead of AMP, cyclic AMP, it's an inhibitor. ATP is an inhibitor, and ATP being an inhibitor is not something which is unique to this step only. We'll see that in the next irreversible step also, ATP is an inhibitor, and the reason for that is, you see, glycolysis itself overall, it's a synthetic pathway, that is, ATP is formed. So if there is already excess ATP, if already excess ATP is present, then obviously the body would not want that more ATP is formed by glycolysis. So that excess ATP already formed will try to inhibit glycolysis. This is what I think is the reason why ATP inhibits this step. And citrate is another very important inhibitor of this step. Citrate is another very unique inhibitor of this step. Okay, done. Now let's quickly move on to the next step. The next step was the last step, pyruvate kinase to pyruvate. Oh, did I say pyruvate kinase? I'm so sorry. Phosphoenol pyruvate. I'm sorry. To pyruvate. And the enzyme required here is pyruvate kinase. ATP is obviously being formed. Now, the thing is, what actually inhibits this step? So this step is actually, obviously again we have insulin, positively effectors. Insulin, right? We have fructose 1,6-bisphosphate, very important, and very strange also. I don't know the reason for this. I'm yet to research on this, so I apologize. But fructose 1,6-bisphosphate is considered as an activator of pyruvate kinase. Okay. Now, what are about the negative effectors? Negative is obviously again glucagon, right? ATP, see, these are the typical inhibitors, and cyclic AMP. So all the three, they are recurring, right? They are recurring. So in the previous step also we had seen them. Done. So that kind of, I would say, completes the regulation, and that actually completes glycolysis as a whole. Okay, so the next time when we come back, we will talk a little bit about the fructose and galactose metabolism. It's very simple. It's just 2 or 3 steps. We'll go on through them very quickly, and then we will jump on to gluconeogenesis. Okay, so thank you for watching. Thank you.